Welcome back. So we were discussing about the powder metallurgy module, and we have already discussed about the gating and runner design aspects in case of injection molding. So we have discussed about injection molding earlier, but to give you some idea, some more idea about metal and ceramic injection molding. So that we will be discussing today in this class. So so the ceramic injection molding process is basically, it is the raw material preparation that I told you earlier also. So if you consider a flow chart, so then this is the mixing of metal powder plus additive. In case of ceramic injection molding, it is the ceramic plus additive that is mixed. And then once this mixture, that is called feedstock. So that after feedstock preparation, we inject the feedstock. So feedstock is achieved in the mixing stage, and then so feedstock preparation is done. So this is feedstock preparation is done, then we basically do the injection molding of that feedstock within the injection molding machine. So this is how we are injecting into the injection molding machine. So from injection molding, what we are getting? We are getting the green preforms or green compacts of the component geometry that needs to be made, that needs to be fabricated. And once the green compacts are done, so assume that this is a cylindrical disc that we have developed by injection molding. Then basically we need to remove the polymeric ingredients from the green compact, so that we can achieve a dense ceramic or metal part. So in case of CIF, it is of course the ceramic. So then we have to do the debinding. So we need to start with the solvent debinding process, where we need to dip the this green compact into appropriate solvent, which are capable of dissolving the polymeric ingredients, which can be, like, for example, one of the binder can be PEG. If it is polyethylene glycol, then it is even dissolvable in water. So in that case, water can be used, distilled water can be used for solvent debinding. And in case of polymers which are not soluble in water, then we have to use N-heptane or N-hexane. So this kind of dissolving media. So after solvent debinding, we do thermal debinding of the part, so that a porous channel can be prepared within the powder component. So you can see, so these are the porous channels that are getting built within the neighboring powder particles. So then these are the channels which are later on responsible for sintering densification. So these are the channels which are responsible for removal of the residual binder present in the this ceramic polymer mixture in the form of vaporization, and then during final sintering state we find a dense structure with minimum porosity, and this is how the injection molding works. Okay. So then additional processing is needed only in cases where the goal is not met by net shape processing, and we need to do the post finishing operations like machining or lapping or grinding. That kind of operations are needed to achieve the final part geometry. So only for those cases we talk about post finishing operations, but otherwise it is the sintering which serves as the last and final step for ceramic injection molding to achieve the desired component geometry. Okay. So so there are different segments, like we have discussed about the process, and then if we talk about the important takeaways like injection unit. So the injection unit handles the feeding, melting and injecting of the raw plastic material or polymer metal or polymer ceramic mixture into the mold. And screw is relevant in case of screw based machines. So there are two kind of injection molding machines that can be utilized for the purpose of ceramic injection molding. So number one is screw based, and another is plunger based. So, one is screw based, another is plunger based. So, in case of screw based machine, so it is basically the screw is rotates and it fluidizes the powder polymer mixture, or mixes it and makes a homogeneous feedstock, and the it moves reciprocally to transport, melt and inject the plastic, and the zones are feed zones like plastic pellets are introduced and conveyed to a forward along a constant root diameter. Transition zone, plastic is compressed and melted as the root diameter of the screw increases. Metering zone, which ensures the plastic melt is uniform in temperature and viscosity and ready for injection. L by D ratio, so it represents the screw's length to diameter ratio, which is typically 20 to 22:1. So, it is basically a typical long cylinder which contains the screw threads, which are responsible for imparting shear force over the polymer metal or the polymer ceramic mixture, and it basically serves the homogenization of the mixture, and also simultaneously it facilitates feeding the mixture, the feedstock material into the mold cavity via injection nozzle. Okay. So, the compression ratio, so it is the ratio of channel depth in the feed zone to that in the metering zone, which is typically 1.5 to 4:1, and it also controls how much the material is compressed and melted. And then the barrel, so it is the hardened steel cylinder housing the rotating screw. So, it is on the top of this rotating. So, it is the annular space in the barrel between the rotating screw and the barrel itself, where the feedstock material is basically undergoes a shear flow, and then it basically moves into the nozzle in into the sprue bush by the nozzle entry. So, this is how it then it basically enters into the component cavity. So, this is a typical layout of the injection molding configuration. This is how it happens, and barrel is the object where we basically incorporate the feedstock pellets, and which are basically undergoes mixing and also melting of the binder ingredients takes place, and thereby we achieve the homogeneous feedstock, and which is subsequently injected via nozzle. So, this is the nozzle. Okay. So, the mold unit, and that is the mold unit shapes the molten plastic into the desired part. So, it is basically the cavity impression is kept there, where from we get the component with the desired geometrical features attributes, and the mold, it is composed of two halves. So, core it is the male part, so projects into the die cavity and shapes the inside of the part, that is core, and then cavity, it is the female part, forms the outer surface of the part, and the molding. So, the gap between the core and the cavity is the region when the defines the final shape of the molded product. And mold feed system, so sprue, so a passage connecting the nozzle to the runner system is basically the sprue that we have discussed several times earlier, and so also we have discussed the runner, which basically takes the melt from the sprue base and transports it to the ingate, and from ingate is the cross section from where it enters into the component cavity. And the cooling system, so it is the water circulation through passages in the mold. So, remove the excess heat and ensuring the molded part solidifies at a quick and timely manner. And the ejection system is, so it is the mechanism which is housed in the it is housed in the fixed half of the mold, and which is responsible for ejecting out the component after undergoing solidification of the polymer ingredients within the die cavity, and thereby freezing of the part, the green compact formation. Okay. So, then so this is, and then the clamping system. So, the clamping system provides the force to keep the mold closed during injection, and clamp exerts force to prevent the mold from opening due to high injection pressure, and also opens the mold at the end of the cycle to release the part. And then the toggle, so it is a clamping mechanism that uses a knee joint principle to apply force, ensures precise closure and opening of the mold. So, this is as a whole the injection molding unit, where you can see that this is the we have individually discussed about individual parts like the hopper, like the screw and the barrel, where I mean the screw rotates and pushes it into the nozzle entry. So, this is the nozzle entry, and then I mean so I mean from here it is basically entering into the sprue. So, this is the sprue. So, which takes the melt from the nozzle, and it has to be ensured that none of the melt gets leaked, and that is why this entry diameter is kept slightly bigger than the nozzle exit diameter, sprue inlet diameter, and then this is the mold cavity, that is this is the mold. So, this is how the clamping mechanism. So, this is the clamping unit which keeps the mold in a locked condition during filling of the mold by the this injection that polymer or the polymer metal or polymer ceramic mixture. And then there are hydraulic clamping. So, this is a clamping system activated by hydraulic cylinder. So, the ram of the hydraulic system is connected to the moving platen which closes or opens the mold. So, it is incidentally it is the moving platen which is also connected with the nozzle of the injection molding machine. So, after it the component gets solidified, again the same platen that moves out, and then the ejection happens. So, the operation is closing. So, pressurized oil enters the cylinder, pushing the ram forward to move the platen and close the mold, and opening oil exits the cylinder, retracting the arm to open the mold. So, this is the movable hub which is responsible for filling of the mold and also then facilitating its ejection, and it is the fixed hub that is generally houses the component cavity and where also the injection unit is mounted. Okay. So, the injection molding process cycle, it is the clamping and then injection. So, we have discussed all of it, and which is again shown here in the form of schematic, where the cooling, the molten plastic solidifies inside the mold cavity. As it cools, the gate freezes up to prevent backflow, and the screw begins retracting to plasticize material for the next cycle. So, this is what is shown here, and then at the second stage it is the ejection. The mold opens and the part is ejected using an ejection mechanism. So, there are two things which are most important here. So, there must be a injection mechanism to feed the liquid melt or the polymer metal polymer ceramic mixture, and there has to be a ejection mechanism which is responsible for taking out the green compact post injection is done. So, these are the two important functions of the injection molding machine, and then critical notes. So, the hydraulic clamping system ensures precise control of mold opening and closing, which is essential for maintaining part quality and preventing defects, and cooling and gate freezing are crucial to maintaining the dimensional accuracy of the molded part, and the process cycle is basically it works like this. So, first is clamping, then injection, then cooling and green compact development, then ejection of the green compact, and then refilling. So, this is how in cyclic manner the process moves, and the metal injection molding process is pretty similar, only difference being the replacing the ceramic powder. In this case the metal powder is incorporated or mixed with the polymer, and the purpose is producing small complex high volume components, and the process steps are pretty same as we have discussed in case of ceramic injection molding. And then so, this is the only difference is that in case of sintering, in case of sintering, although in case of ceramic also which are oxide ceramics which does not react with the oxygen or does not get oxidized further, we still use some inert gases to flush out the effluent, that means the polymeric ingredients that goes comes out during debinding. However, for sintering stage it may not be necessary to create the gas environment. However, in case of metals, because this is very much they are very much prone to get oxidized. So, we have to do the sintering, it has to be performed in a inert gas environment or in a vacuum environment. So, which is a key difference in case of between metal and ceramic injection molding. And another thing is that because of these chances of oxidation and the chances of warpage is also higher in case of metal injection molding, and which can lead to higher tendency for defect generation in case of metal injection molding. Hence, the process has to be carefully controlled, and the gating geometry has to be carefully designed in case of metal injection molding. So, the outcome so it is also possible to do liquid phase sintering in this case, like in case of ceramic injection molding. And temperature example, stainless steel is sintered around 1350 to 1400 degree centigrade, and again it has to be maintained a typical gaseous inert gas or the vacuum environment to avoid oxidation, which can cause rejection of the sintered part, and then outcome is densification increases to 96 to 99% of the solid density. So, typically 98 to 99% of the theoretical density of the part can be achieved by injection molding route, MIM or CIM route, and that is why it is one of the widely practiced powder metallurgy technique and one of the best also in the class. So, this is why it is this injection molding has a wide applicability. So with this we are done with the powder metallurgy module. So, we will meet next for the process modeling part of the powder metallurgy module. So, till then thank you and bye, goodbye.